The next cipher we're going to look at gives us perfect security, and it's called the use of one-time pads. So first we're going to review some of the weaknesses in encryption security in the ciphers that we've studied up until now. Then we're going to introduce what one-time pads are and explain why they give us perfect security. We'll do a sample encryption and decryption, and finally discuss some drawbacks of one-time pads despite their good security. So first of all, every cipher we have encountered so far has been relatively insecure. So for monoalphabetic ciphers, those are vulnerable to frequency analysis. The transposition ciphers, we haven't talked a lot about what those weaknesses are, but they do have weaknesses. First of all, they contain the exact same letters in the original message, so they can be detected using frequency analysis. If the frequency of the letters is the same as you'd expect in an ordinary message, you can guess that it's probably a transposition. And these can also then, once we know that they're transpositions, they can be decrypted using various techniques called anagramming and some other computational algorithms as well. For polyalphabetic ciphers, those have some promise, but a lot of them have some structure, very similar to what we had in the Vigenère cipher. And so what happens is you can use this structure to find patterns in the message and then eventually reduce it to frequency analysis. What we really want for a cipher with perfect security is we want a polyalphabetic cipher, but we want a truly random key that doesn't have any patterns in it that can be exploited. And we get that in a cipher called one-time pads. So here's how a one-time pad works. So the key is going to be not a keyword, but a random sequence of characters that is at least as long as a plain text message. So this is if you had a plain text message of 100 characters, that means your key would have to have at least 100 characters. So big key. For encryption, first thing you're going to do is you're going to match up each character in your plain text with the corresponding character in the key. So you're going to pair them up, one in plain text for each character in the key. Then you're going to apply some predetermined rule to each matched up pair of the characters. The rule we're going to use is that we're going to take their numerical representations, 0 to 25, add them up, and then mod out by 26. For decryption, you do the exact same process in reverse. And then here, this is key. Our big requirement for security is that we have to use a different key for every single message. So it's not like you have one key of random sequence of characters that you can use for a lot of messages. You literally use that random sequence of characters for one message, you throw it away, and you never ever use it again. So if we use one-time pads properly, then we have perfect security. In other words, the cryptanalyst cannot decrypt the message at all without having the key. All right, so as I mentioned before, in our class, the rule that we're going to use to encrypt our messages is we're going to represent each pair of the key ciphertext characters as numbers. We're going to add them together and then mod out by 26. So if we want to encrypt a message, say here's our plain text Agatha all along, and suppose we have this key DHYFHJTYVJDIRF, which I obtained by just randomly hitting keys on the keyboard, and it just happens to be just as long as the plain text. That's kind of convenient. What we're going to do then is pair each letter of the message, so you can see the plain text message is on the top row, and then the key is on the bottom row, and so if you look at the columns, that's how we're pairing up the letters. So what we're going to do is we're going to convert the message, the plain text message, into numbers. We're going to convert the key also into numbers, and then we're just going to add vertically. We're going to add the 0 and the 3, the 7 and the 6, the 24 and the 0, the 19 and the 5, etc. Notice that some of those numbers go above 26, so we're going to have to mod out by 26 to make them in a form that we can actually get letters from them. And then we're going to convert those numbers back into letters to give us the ciphertext, and we end up with DNYYOJTJGJOWEL for our ciphertext. If we want to do decryptions, let's say we have the ciphertext QHAVHYADM, and we have the key FHGIFRLDJ. Now, again, the key and the ciphertext happen to have the same length, so again, we're going to sort of line them up, the ciphertext on the top and the key on the bottom. We're going to take the ciphertext and convert that into numbers. That's the 16, 7, 0, 21, 7, 24, 0, 3, and 12. We're going to do the same thing with the key. Then, since we're going, the way we got the ciphertext was we took the plain text and added the key to it. Now, in order to reverse that process, we're going to have to subtract the key from the ciphertext to get the plain text, and then mod out by 26. So I did both of the processes at the same time. You can see most of them were just regular subtraction. 16 minus 5 is 11. 7 minus 7 is 0. But then we get to 0 minus 6. That literally is negative 6. But when we mod out by 26, we get 20. 21 minus 8 is 13, 7 minus 5 is 12, 24 minus 17 is 7. Here we have another one that's negative 0 minus 11 is negative 11, which is 15 when you take it mod 26, and the rest of them are just plain old subtraction. And then you take those and you convert them back into letters, and you end up with the plain text Launchpad. So I want to talk a little bit about the drawbacks of one-time pads. It may seem really exciting that we actually have found a cipher that gives us perfect security. That's kind of what we were looking for all along. But there are some serious things we have to consider before using this as an actual cipher. First thing is, I mentioned that using the same key twice is a big no-no. And what happens is if you use the same key twice, then your messages become vulnerable to cryptanalysis. There are certain techniques that you can use on when you use the same key twice. So you have to use the same different key for every single message. And if you're sending lots of messages, that's a lot of keys. So that can be really cumbersome. The second thing is the keys need to be random. It's not like the keywords that we had in some of the other ciphers where you could just memorize a keyword and use that to generate some other kind of key to generate your cipher. And that means you can't really memorize them. I mean, especially if you have keys that are hundreds of characters long, there's no way a human being will be able to memorize those and keep them in check, which means that it'll be difficult to encrypt and decrypt messages. And so the big deal here with all these leads us to the need to distribute usually huge books or computer files with the keys written in these books or files in the correct order so that people will know. And not only that, but they have to also keep track of who's sending messages. Because if someone else sends a message with one of the keys, that means you can't use that key either. So we have huge numbers of keys that have to be used. So if you have extremely high security needs, then this might be worth the extra expense. But unless you have really, really high security needs, the cost of implementing one-time pads is usually pretty prohibitive. All right, so now I think you're ready to work on your own one-time pad encryption and decryption, and that's going to be on the PDF file included with this video.